So let's remember how to add and subtract fractions so that when they ask us to do this in an algebra problem, we have a really good idea about what it is that we have to do. So if I take a look at this first problem and I ask you to add together 1/4 plus 5/4, and I asked you what is that special condition that needs to be true whenever we add and subtract fractions? If you think about it, the one thing that always has to be true is that the denominators have to be the same. It's what we call common denominators. So in this case, I have that situation. I can say this is 4 and 4, so I can just add across the top. This becomes 1 plus 5 is 6 over 4. So remember what we did. We added across the top of the fraction, and we left the bottom of the fraction alone. And then again, I can simplify this to 3/2. Okay, so if I ask you to add together 1/4 plus 5/4, your final answer in simplest form is 3/2. Okay, if I take a look at the second one, it is not in simplest form. And I'm pretty sure you could look at this and tell me that the 6 and the 4 have a 12 in common. That is a common multiple and the least common factor. So the question really is, how do I get that when I'm looking at an algebra problem and I can't really look at them and figure out what's small and what's big, right? So here's really what you're doing when you're taking numbers like 6 and 4. I'm really going to take 6 and I'm going to break this up into 3 times 2. Okay, and I'm going to look at the 4 and I'm going to break that up into 4 times 4. I'm sorry, 2 times 2. Okay, and I'm going to just bring along the denominators. So let's make this a 2 times 2, right? And I have a 1 up here and a 5 over here. So I just rewrote this expression, but I factored the denominators. When you're finding the least common denominator, what you're really doing is figuring out what is in this denominator that's missing from this denominator. So if you notice, this one has a 3 in it. This one doesn't have any 3's in it. So I'm going to multiply a 3 on the bottom here, so I can at least say both of my fractions have a 3 in the denominator. But remember, whenever we change fractions and we multiply something in the denominator, I also have to multiply that something in the numerator. Right? So I'm multiplying now by 3/3, and I'm not changing the value of my fraction. Right? So now I'm going to compare again. I'm going to look at this and say, wait, this one has a 2 and a 2 and a 3. This one only has a 1, 2, and 1, 3. So now it looks like I'm missing a 2, and so I'm going to bring in a 2 here in the numerator and the denominator. And now I'm going to simplify these pieces. It looks like 3 times 2 is 4. 3 times 2 is 6. 6 times 2 is 12. And there's that least common denominator of 12 that we were talking about. So really what you're doing is a comparison of the fractions in each denominator and seeing what's missing and making sure that that missing factor gets brought into the denominator. Okay, so if I put this back together, 3 times 2 times 2, well, that's 12. 2 times 1 on the top. Now, if you notice, it became from 1/6 to 2/12. That got fixed. And I got, it looks like 15 over 12 in the denominator. Right? So it looks like this becomes 15 plus 2, which is 17 over 12. And that would be my final answer. There's no way to reduce that. But again, big idea, what I did was I factored the denominators, and I compared what was missing in one but that was present in the other, right? And then I brought those new factors into the problem. So let's look at that with some algebra problems, okay? So we'll start off with the easy ones, right? If I give you a problem that looks like this, and I say add together these two rational expressions, really we're just going to look at the denominators, say, okay, in this case they match. We're good. I don't have to do a whole lot. Okay, so I'm going to say in this case 9x plus 2x is 11x. Okay, and I'm going to leave the denominator alone. I'm not going to add together the denominators and say that that's 2x plus 14. Denominator stays the same, x plus 7. Okay, and now here's the catch. Whenever I do any rational expression problem, I need to make sure that it is in simplest form. So I need to take a look at 11x over x plus 7 and be sure that there is nothing that cancels, and in this case there's not. Remember, this x is a factor, but this x is not a factor, so I can't cancel those ones, okay? But I do have to do a check and make sure that we're good. So let's take a look at the next one. So it's the same idea, 7x minus 4x plus 12. The denominators are the same, so I can say that's good. Let's bring that along. That's not going to change. Now here's where we have to be careful. This minus sign, okay, is really applying to the entire 4x plus 12. So I'm saying 7x minus 4x. All right, well, that's pretty easy. That's 3x. Okay, but this is really also saying negative 12, right? So negative 12, because this is technically like plus 0, and I'm saying 0 minus 12, and that's a negative 12, right? So you have to be really careful that if you want, you can distribute the negative inside, or you can think about it as a 0 minus 12, but in any case, the 12 is going to be negative in our answer. So be careful with subtraction that you make sure to apply the minus sign to the entire expression, not just the first term. Okay, so now I have this answer, 3x minus 12. And we have an issue, because 3x minus 12 is actually factorable, and it factors into 3 times x minus 4, and if you notice, it is over an x minus 4, and I get this common denominator situation, and I get this common factor situation with the numerator and the denominator that will cancel, and my final answer is actually just 3, right? Everything canceled. So even after I subtract, I may need to factor expressions and do some canceling, right? So let's do one more of these, right? So again, I have this situation where it's x squared minus 9, okay, a little bit easier, and on the bottom I have x minus 3 as my common denominator. That's going to just repeat, and this turns into x plus 3 and x minus 3. I actually do a pretty complex factor there. Right? That's not as simple as GCF, right? And I have that x minus 3 on the bottom, and so now I can say x minus 3 and x minus 3. X plus 3 is my final answer, right? So let me state this. In previous videos, we've talked about domain restrictions, so I'm not going to keep harping on the point and keep stating them, but anytime we do any of these problems, you should state a domain restriction. So for my first problem, I should say x is not equal to negative 7, x is not equal to 4, x is not equal to 3 for all of these problems, but I'm not going to continue to do that because I think you have a good idea of it. All right, so now I'm going to look at this situation, and we're going to say, well, now the denominators are different, so I can't just subtract or add like we did in the previous problems. So when I look at these, I'm going to look at the left expression, right, 4 over x minus 5, and we're going to say, all right, what's in this expression but that's missing over here, right? And so I'm looking for a common denominator. I'm going to say x minus 5 is present here, but if I compare it to the other fraction, this one has an x plus 1 that isn't in my first expression, so I'm actually going to add it in there and say I need this expression, right? I need one of each factor from everywhere along the denominator, and I'm not going to do a lot of repeating, okay? So I'm going to say, to compare that, well, this one has an x plus 1, but it's missing the x minus 5 that was in the other one, so I'm going to bring that over here. And if you remember, that's very similar to what we did in our example here. We said I had a 3 and a 2, but I was missing something from the other fraction, so I brought it over. Here I had a 2 and a 2, but I was missing the 2 on the other one. So we actually brought it over, right? And we made sure that in both of my fractions, both of the factors were present, okay? So now I'm going to look at this and say, all right, there was a 4. My original expression had an x minus 5 in it, which means it looks like the new thing is this x plus 1, so I need to multiply that on the top as well. Okay, and I'm going to do the same thing over here. It had an x plus 1. Right, the 2's on the top already. The x plus 1 was present. I brought in this brand new expression x minus 5, so I need to make sure that that shows up in the numerator as well. Right, so let's simplify these. I'm going to get these other problems out of the way because we're not going to do all of them. Okay, so let me move this down. So I'm going to take a look at this and say, all right, now it says if I distribute 4x plus 4 over, and again, don't worry about multiplying these together. Leave it in its factored form. We're going to call this x minus 5 and x plus 1. Okay, and on my other one, I have my other fraction. I have 2x minus 10 over x plus 1 and x minus 5. Okay, so now I can subtract. Again, we're going to be careful. 4x minus 2x. 4x minus 2x is 6x. I'm sorry, it is 2x. Okay, and here's where we have to be careful. Well, apparently I can't write today. Okay, 2x. Okay, and then 4 minus negative 10. 4 minus negative 10 is 14. Okay, so I'm going to say plus 14. Okay, so be careful. 4 minus negative 10 is like 4 plus 10. And this is all over x minus 5, okay, and x plus 1. So here's one of the reasons that we didn't multiply together the denominator, because now I can look at the factors that were in the denominator, the x minus 5 and the x plus 1, and make sure that neither of those factors is present in the numerator, because then we'd have to do some simplifying. So I'm going to say in this case, this is really 2 times x plus 7 if I were to GCF out that 2, and I don't have an x plus 7 in the denominator, so I'm good. This is my final answer. Okay, so you can see it's a little bit trickier here. We have to make sure that both of the factors that were showing up in the denominator are present, okay, in our common denominator. So let's do one more just to get the idea. This is definitely a little trickier than just adding across the top like we did in the last problems. Okay, so your second problem, I'm going to do the same thing. I'm going to look at this and say common denominator. This one has an x plus 3, so that's going to stick around. Okay, this one has an x minus 2 that needs to come over to the first one. Okay? And so I'm going to look at the second one and say, all right, this one has an x minus 2. The one on the left has an x plus 3, so that's got to come over and be present in my second one. And so now if I take a look at them, now they're common, right? So I just brought the missing factor from each of them, and I brought them into the fractions, okay? So now I'm going to look at this and say, all right, this has a 5 in the numerator. That was there at the beginning. It had the x plus 3. My new factor is x minus 2, so that's what needs to be multiplied on top. And in the second fraction, it's the opposite. The x minus 2 was present, okay? So I'm going to bring in this new x plus 3. Okay? So I'm just bringing in whatever I brought in that was brand new into the fraction, into both the numerator and the denominator. Right? And here's something that a lot of people want to do with these. They look at it and say, look, x minus 2 over x minus 2, let me cancel those. We're not going to cancel them because we just made that happen. We just brought those in as brand new into the problem. If I canceled and canceled and canceled and canceled like it looks like I want to do, what I'm going to do is end up with denominators that aren't common anymore. Okay, so we can't do that. Right? And again, if you take a look back at our regular problems, we actually turn things that are reduced like 1/6 into things that aren't reduced like 2/12 so that we can then add like we couldn't before. So don't cancel out the x minus 2's. That's a very common thing that people want to do. So now that I have my common denominators, again, I'm just going to leave those. Hey, let's go back to blue. X plus 3 and x minus 2. That's going to stay as my denominators for both of my fractions. And I'm going to look at my numerators and say, okay, this is 5x minus 10. And this is x squared plus 3x. So now I got to add these together. Let's see what happens. I have x squared. I'm going to put them in standard form as I go. So it's positive x squared. And it looks like 5x plus 3x. Well, that's 8x. Okay. And then the minus 10, and I don't see anything to change that, so that's going to stay as minus 10. All right. And my denominator stays the same, x plus 3 and x minus 2. Right. That's my new denominator. And I'm just going to take a quick check again at this numerator. That looks like something that we can factor. So let's check. If there's anything that multiplies to negative 10 that adds up to 8, I'm going to try to factor it. In this case, we're lucky there is not. So this is not a factorable expression, and I'm done. Right. So again, this is my final answer. And again, the domain restrictions that we're not listing would be x is not allowed to be equal to negative 3, and x is not allowed to be equal to positive 2.